Hi everybody, my name's Christopher Collison, and today we're going to go through a spreadsheet that we're going to use to help us build our prototype for the heat pack that will hopefully save someone's life from frostbite and certainly save their hand. So follow along with the Excel spreadsheet and think about each step of the way. Think about all the measurements that you're going to make and see how they fit into the Excel spreadsheet. Write down all the measurements that you're going to make before you look through the video, and make sure you can really understand how each of these pieces are going to be used in two fairly straightforward equations. One, the heat associated with the reaction is going to be equal to minus the heat taken up by the water, and then equal to minus the heat ultimately taken up by the hand. So that's our first equation, and that comes from the first law of thermodynamics. And the second equation is really just the proportionality between the heat and mass and specific heat capacity and the change in temperature. So that equation would be Q equals mc times delta T. Fairly simple, but fairly complicated and complex connections of all these particular measurements. So see how this all works in Excel, and bring this Excel spreadsheet with you to class for your lab. I hope you benefit immensely from watching this video. Thank you. So what I'm going to start with is just a blank piece of paper, a blank worksheet in Microsoft Excel, and I'm going to start thinking about the different measurements that I'm making in various parts of the experiment. And what I want you to do is follow along with your own notes and with your own paraphrasing of the procedure that you have in front of you. So first of all, we're going to start in column B and row 2, give ourselves a little bit of space either side, and I'm going to actually write down the mass of the water that we start with in the beginning of the experiment. To give myself some space, I'm also going to put the quantity down here in column D. So that would be 100, and I'm going to put the units next to it here. You will want to tidy up your spreadsheet when you submit this, but we have to start somewhere, and this is the way I propose starting. I would absolutely need to see how you've changed the spreadsheet so that it's able to be graded by your professor, but this is how we're going to start, and this is how I want to talk you through the process. We also recognize that we're going to have an initial temperature of the water that we start with. And I'm going to make these numbers up, but I'm going to put in a number initially that's about room temperature, maybe cool, but that'd be in degrees Celsius. So I'm entering that number, and I'm going to again put my units in here as best I can and as quickly as I can. I'm also going to enter in here the temperature of it's going to be the initial temperature, in fact, of the sausage. So we'll change that around in here. And we know that that sausage is going to be in an ice bath, so we know that the temperature is going to be 0 degrees Celsius. We're going to add the sausage to water, and then of course we're going to get a final temperature, so we'll call that T final. And that final temperature, by the way, is going to be of the water and the sausage. And we're going to add that value in here. I'm again making this up. So let's say that we reduce the temperature of the water to 17.3, and again that would be in degrees Celsius. So what do we have? What are we thinking about at this point? So what we need to consider is that the heat of the water is going to be based on our 100 grams of water that we have to begin with, multiplied by our specific heat capacity of that water. And now we're going to multiply that by the final temperature of the water, 17.3 minus 19.9 degrees Celsius. So we're going to put that into an equation in Excel. So we will write down here Q of the water. And again, we're going to set our equal sign in here. And this is going to be the mass of the water. The mass of the water indeed is found in cell D2. And then we're going to multiply that by the specific heat capacity of the water. That is going to be, we're going to put this up here actually in a new cell. So we'll put that in cell H3 in a second. And then we're also going to multiply that by the temperature difference. So we're going to have our final solution temperature, which is 17.3. And that's going to be minus the initial temperature of the water in here. So of course this is going to return a 0 value at the moment until we end up putting a value for the specific heat capacity into H3. So that would be 4.18, and that would be joules per degrees Celsius per gram. And we'll call this the specific heat of the water. Okay, so now we have the Q of our water. If we want to find the specific heat capacity of our sausage, well, how will we do that? Well, again, we're going to remember our simple expression. So Q sausage is equal to 35 grams. In this case, so we imagine the sausage, we know the sausage mass, we've weighed the sausage mass, so we're going to multiply that by our unknown, which is going to be our specific heat of the sausage, multiplied now by our final temperature of the sausage, which is 17.3, minus its initial temperature, which is 0. So, of course, we are going to recognize that the heat of this sausage, by the way, Q sausage, is equal to minus Q water. Okay, so let's put that into Excel now. So Q sausage, we know that is going to be equals minus the value that we found in the water here. There we go. And now all we need to do is find out what the specific heat capacity for our sausage is. And so now we do some algebra. So we're going to say that's equal to the heat of the sausage. We're going to divide that by the mass of the sausage. So we have the mass of the sausage up here. And let's make sure we do this correctly in Excel. I always like to put things in brackets if it's uncertain to me how Excel does the calculation. But we're also going to multiply this term by the change in temperature, and that change in temperature, by the way, is again our initial temperature, our final temperature of 17.3 minus 0 in this case. So we can plug those numbers in. How could we do this actually better? We're going to refer back to the temperatures that we've got in our cells above. So here's temperature and a new temperature. Here is our initial temperature up here, and we're going to, put the brackets in here, and we will fix this error by saying this is the mass of the sausage, and that we are claiming is 35, and that is in grams. So now what we have is something where we have the specific heat capacity for our sausage. I'm making these numbers up, so you'll end up having your own numbers as we go further forward. We can also, by the way, double click on this column width in here, and that allows me to see the text that I've written in here. So that's pretty much part one, and we're actually going to label these sections of our Excel spreadsheet and try to keep things reasonably well organized as we build a spreadsheet. So let's jump to part two, and let's remind ourselves what we're doing in part two. In part two, we're actually trying to calculate the enthalpy of reaction for 1 mole of dissolving our salt in water. So again, we're going to start with a mass of the water, and let's just imagine that again we're starting with 100 grams of that material. We're also going to have an initial temperature. Again, in this case I'm just going to copy and paste, and what we'll say, let's mix it up a bit in here, let's have a slightly different temperature of 19.6, and that would be degrees Celsius. We're also going to add a certain amount of salt. So let's imagine that the sodium chloride that we add is going to have a certain mass. And let's make that mass randomly. You're of course going to weigh this out. Let's make this be 30 grams. We're also going to have a final temperature that you'll measure. So what's the final temperature? And I'm going to use copy and paste here to help me. The final temperature, this is going to be of the solution now. But we're also going to assume that that solution, by the way, has the same specific heat capacity of water when we come to that. But we're going to assume that we've got a temperature increase and we've gone up to 21.3 degrees Celsius. What else? Well, we're in fairly good shape. Again, we already have our specific heat capacity of water, and we can change our headings for this later. We're just going to keep things moving forward. So what's the heat that's taken up by the water? So we'll do our Q of water again in here. It'll actually be the heat of the new solution now, but we can calculate that as being equal to the mass of the water. So here's the mass of the water multiplied by the specific heat capacity of that water. And that's now going to be multiplied by our final temperature. Our final temperature now is a higher temperature because the salt has heated up that water through its dissolving. And we're going to do D14 minus the initial temperature. And there we have our heat of the water. Next up, we have to actually recognize that there's been a certain amount of heat that's been released by that salt. So we can actually call this delta H if we want. Another way of writing it perhaps would be, let's do two approaches here, would be Q of the reaction. And this will be the same thing, I'm just writing in two different ways, but the Q of the reaction, by the way, is simply equal to minus the Q of the water. What are these units, by the way? These units are going to be in joules. Delta H is effectively exactly the same thing, is equal to the Q of the water. It's also equal to the Q of the reaction. Sorry, it's equal to minus the Q of the water, and it's equal to the Q of the reaction. So we also have a mass of our salt that we figured out earlier. Another thing I'm going to put over in this column in here now would be the molar mass of sodium chloride rather, and the molar mass of sodium chloride is 57.96, and that is grams per mole. Okay, so what we can also do now here is we can even write down the number of moles of sodium chloride, and that's going to be equal to the mass that we have divided by the molar mass. And there's a number of moles of sodium chloride. So the last piece here is to actually figure out what our enthalpy change would be for 1 mole of sodium chloride being dissolved in water. So how would we calculate? How would we calculate that? So this is going to be the molar heat of solution of sodium chloride, and that's going to simply be equal to the heat that we've calculated, so our Q of our reaction, or our delta H, let's use in this case, divided by the number of moles that we put in there to begin with. And that unit now that we need to use is going to be joules per mole. And effectively, that is the end of part 2. So now comes the tricky bit. We now have to make our assumptions. So we're going to say 1 hand, I'm making these numbers up, is equal to 8 sausages. You are going to do your own estimate. There's no real right answer to this. What we've previously figured out is that 35 grams is equal to 1 sausage. So this is going to give us the mass of our hand as being 8 times 35, which is 280 grams. Okay, so we'll enter that shortly. Okay, we also recognize that in fact this reaction and the heat that's generated in this reaction really has to be greater than, but we're writing equals for now because we're going to play with this a little bit in Excel, is going to be equal to a value that we're going to predict for Q of water. And ultimately we want that heat, as the water heats up, we want that heat to come from the heated water directly into the hand. So let's think about all these things. In fact, I need a minus sign in here because that heat is going from the reaction into the water, which is pretty much the same as going into the hand. Okay, so really it's going into both of these, so we'll consider it in this way in Excel. Let's go back to Excel and have a little look. So part 3, let's start plugging in some numbers in here. So we'll put in the mass of the hand, and that is going to be 280, and that's in grams. We also are going to plug in some numbers on this right hand side, and I'm going to put in here the mass of the water that we're going to end up using. So that's going to be in grams. We also, in fact, need the mass of the sodium chloride that we're going to add, and that is also going to be in grams, but that's also based on our number of moles that we are probably going to need to use, since we have a heat, a molar heat of reaction that we've calculated from part 2. So let's also put the number of moles of sodium chloride in here. And we're going to throw some random numbers in here to begin with. So let's just put 1 mole of sodium chloride in here. And let's start with, say, 50 grams of water. And we'll play with these numbers a little bit later on. But you'll see here that the mass of sodium chloride is going to simply be equal to our molar mass up here multiplied by the number of moles. Okay, and so over here, we're going to transfer our mass of NaCl, and that is going to be equal to the value that's calculated over here on the right hand side. Maybe this step is redundant, but we've got our mass of our hand, we've got the mass of our sodium chloride, and we've got the mass of our water already set up in here. I'm going to highlight these cells as cells that I'm going to vary the numbers in a little later on. This is going to help me as I build my prototype. So, what do we know? We know that our hand has to heat up by a certain amount. So we know the heat that needs to be taken up, and that is also based on, so Q hand is going to be equal to the mass of our hand multiplied by the specific heat capacity of the sausage, which we consider to be the same as the specific heat capacity of our hand, multiplied by that temperature change. Remember, our final temperature, we want to be something like 37 degrees Celsius. And we've got a cold hand to begin with of 15 degrees Celsius. So those numbers are going to get plugged in here. Let's go back to Excel and see how those numbers are calculated. Okay, so we've got the mass of our hand, and we figured out that the mass of the hand was equal to 280 grams. So we can take that from cell D22. We're going to multiply that number by the specific heat capacity of the sausage. Well, we calculated that earlier in the part 1, and it was given up here as 1.79. So we're going to plug that in, and then we're also going to multiply this by the final temperature, and let's plug some numbers for the final temperature actually into cells H25 and H26 for the initial temperature. So we'll do H25 minus H26. I'll show you how this makes sense in a minute. Let's press enter here, and then this is our final temperature of the hand, and we're going to have that be 37, we said, and that's degrees Celsius. And the initial temperature of the hand, and that's going to be 15 degrees Celsius. And lo and behold, we have a number here in joules that is the Q that the hand really must take up in order to avoid this frostbite. So this kind of tells us what heat we need from our reaction to begin with. So what we can certainly do for our reaction to begin with is actually start to write down Q reaction. And we can also think about, in fact, Q of the water that's going to be taken up. Remember, we're dissolving this sodium chloride into some water. And that's how we're going to release the heat from that reaction. But we need these to be, we need the heat of the hand to be equal to minus the heat of the reaction. By the way, we also want, we're expecting the water to take up that heat from the reaction. It's actually going to be about the same as the heat of the hand. So we can equate these two numbers to begin with, and then we'll see what happens after. So we need quite a lot of heat in here. How are we going to get that heat? Let's think about the Q of the reaction and what generates that Q of reaction. Remember, the Q of the reaction is equal to the standard delta H of the reaction, and that's per mole, multiplied by the number of moles that we have, right? So this is going to be really in joules per mole, and when we multiply that by number of moles, then what comes out is an energy in joules. Let's calculate that. So how do we get this Q of reaction? So let's do predicted Q of reaction, and that's simply going to be equal to the number of moles multiplied by our molar heat of solution. We enter that in here, and what we can actually do now for fun is we can compare this predicted heat of reaction with really the needed heat of reaction, and we're finding out that here we're about 10 times short. So it turns out if we believe these numbers, what we need to do is we perhaps need to increase our number of moles. Let's actually take it to 12 in here. Take our number of moles to 12, and now we're giving off 16,474 joules. So that's plenty. So once we've figured out more or less how many moles of sodium chloride we might need, let's actually think about the temperature change that's going to happen in the water. Remember, we started with a mass of water of 50 grams. So let's put the actual or the predicted Q of the water in here. Remember, Q of water is equal to the mass of the water times the specific heat capacity of the water. And in this case, we're going to have a delta T, right? We know our initial temperature of the water. Okay. It's actually going to be TF in here minus TI. We know our initial temperature of the water. Let's assume that our initial temperature of the water is in fact 4 degrees Celsius. We're in a cold place. It's not going to be warm. Hopefully it's not frozen. But let's now think about the heat of the water, and let's try to decide the mass of the water that we're going to want to add to our salt. T of our water initial, so that's 4 degrees Celsius. I wonder what our final temperature is of the water. This will be interesting. So remember, the predicted Q of the water, we need to be 11,056. But we've got to think a little bit about how much water we keep in our bag. If we have too much water, then that water is not going to heat up enough. So let's play around with these numbers a little bit. Let's think about actually what the final temperature is. And let's play with these numbers. In fact, I'm going to change this to now be, I'm going to put this final water temperature over in this column over here. So that final temperature, we rearrange this equation. We are going to have TF final minus T initial is equal to Q over MC. And what we have to do if we want that final temperature is we're going to have to add the initial temperature to both sides, and that's what we'll put into Excel. That final water temperature is going to be equal to the heat of the reaction. So let's take our predicted heat of the reaction in here now, and we're going to divide that by the mass of the water, divide it by the mass of the water multiplied by the specific heat capacity for the water, and we're going to add now to that the initial temperature of the water, and we'll see what comes out. Of course, we need to account for our signs in here. We have to have a minus sign in here because the heat of the water is equal to minus the heat of the reaction. So now we get a number that seems to make more sense. So with 50 grams of water, we might predict, and with 50 grams of water and 12 moles of sodium chloride, we might predict that the final temperature of the water is 82 degrees Celsius or 83 degrees Celsius. So this is reasonable, right? We know that as that water starts to heat up, then our hands holding onto that bag of water are going to be able to take away that temperature, be able to take away that heat from the pack before it makes its way up to 82 or 83 degrees Celsius. So I want you to think through what I've done in this presentation. With this predictor, what we've done is we thought about the mass of the water in here that we want to use in our prototype. We thought about the initial temperature of the water that we might use in our prototype. We've also thought about the number of moles of sodium chloride in here. That's 695 grams of sodium chloride. So maybe that's too much for this particular prototype. So we might have to go back. If we're in the real world of making these things, we'd have to go back and find a better system perhaps, because that's just too heavy to carry around. But you see the point, and with this Excel spreadsheet, you can get to a place where you start to understand the experiment. You bring this Excel spreadsheet with you, you start plugging in the numbers that you actually measure, and you get a prediction of what your prototype will look like. So I've run through this very quickly. You've seen how I've used Excel to actually go through the calculations. This is the best place to start, and then you can modify your spreadsheet so that it ends up being more clearly labeled. But you get the idea that when you've labeled it even in this way, that when you get to lab, you can start plugging in the numbers and you can start getting through the lab in a quicker pace, and we'll get through to that prototype stage, which will be very fulfilling, I promise you. So thanks very much for listening. I hope this helps, and we'll see you in lab.